All right, so this is the first of two lessons looking at eigenvalues and eigenvectors. And just a heads up, you'll probably find aspects of these couple lessons pretty challenging. And so just focusing on one fairly small section today. It's fairly abstract, it takes a bit of practice. And these two phrases, eigenvector and eigenvalue, are easy to mix up. The key is one is a vector, and a vector, well, we'll talk later on in the course, a vector essentially is a simple matrix like this. Like this is a 2x1 matrix. There's other types of vectors, but a vector can be represented as a simple matrix. In this case, we're looking at 2x1 matrices, whereas a value, an eigenvalue, is a real number. So that's a little easier to understand. So one is a vector, which can be represented as a matrix. One is just a value, a real number. And I think the best way of looking at this is just to try it. And so first of all, an eigenvalue is the solution to where the determinant of this equals 0. So what does that mean? Well, let's look at this example here. Here's a fairly simple matrix, and I want to find the eigenvalues. And in general, for a matrix like this, there's either two real eigenvalues, there's two repeated eigenvalues, or two complex eigenvalues. And we need to think about where the determinant of A minus an eigenvalue times an identity matrix equals 0. So what does that mean? And keep in mind, we get two different possibilities here. So they may both be real numbers, they may be complex numbers, they may be the same number. Well, first, A is just 4136, so I'll write this down here, 4136. Subtracted by, this is what we're trying to figure out, an eigenvalue, times the identity matrix. An identity matrix for a 2x2 is just 1, 1 on the diagonal. And so if I just perform a bit of matrix arithmetic here, I get 4 minus, well, if I look at all of this here is really just, actually maybe before I do the subtraction, I'll just write out what this is. But what you see here is the same as 4136, that matrix, minus just lambda times everything inside there, which is lambda 0, 0, lambda. And so when I subtract these, I get 4 minus lambda for one of my elements. I get 1 minus 0, so just 1. I get 3 minus 0, so just 3. And then I get 6 minus lambda for another element, 6 minus lambda. And so this here is what I want to find the determinant of. And keep in mind, this process of getting from here to here is always going to be quite similar. If we don't know what lambda is, it's times that identity matrix. So quite often we can speed this up a bit. That's it. I want to find the determinant of that. And I know the determinant of that will equal 0. So the determinant, remember, is this times this minus this times this. So in this case, it's going to be 4 minus lambda times 6 minus lambda minus 1 times 3. That's the determinant. And keep in mind, the eigenvalues are the solutions where this equals 0. So the eigenvalues are where, again, the solutions for this to make this equal 0. So now we have a polynomial. In fact, we call this the characteristic polynomial of the matrix. And we can solve this using what we've learned about polynomials. I'm going to expand and simplify 4 minus lambda and 6 minus lambda. And I get 24 minus 10 lambda plus lambda squared minus 3 equals 0. Collect like terms, I got a quadratic expression, lambda squared minus 10 lambda plus 21 equals 0. I'm going to try factoring this, and yeah, we can factor it. We get lambda minus 7 and lambda minus 3. And so my two solutions are 3 and 7. Or quite often we can say one of our eigenvalues is 3, lambda 1, and my other eigenvalue is 7. So keep in mind, these are values. These are real numbers. These are not vectors. These are not matrices. These are just values. Okay, and we'll look at later on about what they mean. All right, let's do one more example for this matrix here. Same idea. I need to make the determinant of the same expression here equal to 0. First, though, let's figure out, in this case, what this is. A minus lambda I. And so in this case, that's going to be, if I think of this, it's going to be minus lambda times this same identity matrix. And again, if I multiply lambda into here, then that just becomes lambda, and that becomes lambda. So really, we can think of this quickly as this. And then ideally, we can do this quite quickly. 3 minus lambda. So I want to think about 3 minus lambda. Negative 2 minus 0 is negative 2. 4 minus 0 is 4. And negative 1 minus lambda is negative 1 minus lambda. So this here is this. Keep in mind, I know the determinant of this must equal 0. So I know the determinant of this must equal 0. And so likewise, determinant is this times this minus this times this. Got a lot of negatives here. And I know that determinant must equal 0. That's the definition of what will make an eigenvalue. Clean this up a bit. Fairly quickly, I get to lambda squared minus 2 lambda plus 5 equals 0. This does not factor, so use the quadratic formula. So I'll say lambda equals minus b, so 2 plus or minus the square root of my discriminant. In this case, I should get a discriminant of negative 16 over 2. Keep in mind, we said the eigenvalue could be a complex number, and that's what we have here. So I can rewrite this now as 2 plus or minus root negative 16 is the same as 4i over 2. Divide everything by 2. My two eigenvalues are 1 plus or minus 2i. So in this case, I had 2 complex eigenvalues. Up here, we had 2 real eigenvalues. Okay, what do these mean? Well, let's look at this question. I want to go back to that first matrix, the one with the 2 real eigenvalues, 3 and 7. Well, before I do that, I need to figure out the eigenvectors. And so an eigenvector is the solution to this equation, where A minus the eigenvalue times the identity matrix times X, which is a vector. So in this case, it's going to be a 2-by-1 vector, or 2-by-1 matrix, equals 0. So now we're dealing with vectors here, not just the determinant. And so what does this mean again? Keep in mind again, I've solved for my 2 eigenvalues, and keep in mind this X is a vector, or it's a 2-by-1 matrix. It's not a real number. And so let's start with our eigenvalue of 3. Okay, I call that eigenvalue 1. Well, I want to go A minus 3 times the identity matrix. So in this case, I have 4, 1, 3, 6. Minus 3 times the identity matrix, that's 3, 3, 0, 0. Which means I can put this together quite nicely and get 4 minus 3 is 1, 1 minus 0 is 1, 3 minus 0 is 3, 6 minus 3 is 3. Everything I see here is what I have here. And so an eigenvector is what I'm going to try to solve for. It's this times x equals 0. Let me clean this up a bit. But that x, again, is a vector. It's a matrix. In this case, it's a 2-by-1 matrix. So I'm going to call it x and y. But I know this must equal 0, but not the number 0, an empty matrix, like a matrix of just zeros. In this case, it has to be 0, 0. And so how do I solve this? Well, let's use our matrix multiplication. 1 times x plus 1 times y must equal 0. So x plus y must equal 0. And over here, 3 times x plus 3 times y must also equal 0. And we should always come up with 2 equations that are equivalent to one another. But what do we do here? We can't solve this system. There's an infinite number of solutions. We just want to see how x and y compare. And so if I solve for x and any of them, I get x equals negative y, which means one possible eigenvector will be any vector of the form in which, for whatever x is, y is just the opposite number. So for example, one possible eigenvector. So x1, one possibility is, I don't know, pick a number for x. How about 1? That means the second value, the y, must be negative 1. And there's an infinite number of possibilities as long as x equals negative y. So another possibility let's go crazy and make x negative 2. And so if x is negative 2, then y is the opposite of that. Y is positive 2. And I could spend the rest of my life coming up with different possible eigenvectors. There's an infinite number of possible eigenvectors for a single eigenvalue. All right. And I still haven't told you what this represents. But that said, I have found 2 different eigenvectors for this one particular eigenvalue. All right. Let's now try same idea. That was a messy squiggly line. For my other eigenvalue, which was 7. Right, so same idea. I want to take my A and go minus now, instead of 3 times the identity matrix, I want 7 times the identity matrix. And so pretty quickly I should go 7, it should be 4 minus, this will be a 7, and this will be a 7. So without making too much of a mess of things, I should get, when I go this part here, I should get negative 3, 1, 3, negative 1. Keep in mind that is not A, that is A minus 7 times the identity matrix. And again, X right here is not a number, it's a vector, it's a matrix, and it's, so again, I'm trying to figure out what those are. But if this really is an eigenvector, this should multiply to make a matrix of just 0. And so like before, now I can use matrix multiplication to come up with a couple of equations that should be equivalent to one another. I go negative 3 times x plus y should equal 0. And notice I get 3 times x minus y equals 0. There's some construction going on outside my room. I don't know if you hear that or not. Notice these 2 equations are equivalent, so I'll just solve for x or y. I don't know, actually, if I look at this one, if I solve for y, I get y equals 3x. And there's various combinations of that. I kind of like that one there, which means a possible eigenvector for this eigenvalue is, this time, if I just pick any number for x, how about 1? Y will be 3 times that. Or if I pick a different one, what if I make x a negative number, negative 2? Y is going to be 3 times that, negative 6. And I could go on and on and on. And so again, these are 2 examples of eigenvectors for the same eigenvalue. So what does that mean? Well, if we do have, for any pair of eigenvectors and eigenvalues, this should be true. The matrix times the eigenvector should be the same as the eigenvalue times that same eigenvector. Okay, so let's look at the example for lambda 1 equals 3. And let me pick one of these 2 matrices. I'll pick this one here. So when we have an eigenvalue of 3, one of my possible eigenvectors was 1 over negative 1. Okay, so how can I show this is true? Well, matrix A, we've worked with a few times. 4, 1, 3, 6. If I take this and multiply by my eigenvector, 1, negative 1, it should be the same as my eigenvalue, which is a real number, 3, times that same vector. It should always be true. And let's just see. It should be pretty quick to see if it's true. For example, 4 times 1 plus 1 times negative 3. So 4 minus 1 should equal 3 times 1, which is 3. And it does. And right here, 3 times 1, which is 3, plus 6 times negative 1, which is negative 6, should equal negative 3. Should equal that part, which it does. And so keep in mind, if I picked this eigenvector instead and put that there and that there, this would still work. Any eigenvector would work for that value of 3. And there's an infinite number of possibilities. All right, so let's try that that was for the eigenvalue of 3. Let's try for the eigenvalue of 7. And let me pick this second one, because again, it doesn't matter. All right, so I know if I take matrix A, which again, I have been using for quite a while now, and I multiply by the eigenvector, I've chosen this one, so negative 2, negative 6. That should work if I take my eigenvalue, which is 7, the number 7, times that same matrix. Oh, the construction's getting close to me. I better finish this video soon. And keep in mind again, if I look at my matrix multiplication, I get 4 times negative 2, which is negative 8, plus 1 times negative 6, which is negative 6, equals 7 times negative 2, which is negative 14. And that's correct. And I should check with both. 3 times negative 2 is negative 6, plus 6 times negative 6 is negative 36, and that should equal 7 times negative 6, which is negative 42. So good. I've not made a mistake. I've not lied to you. And keep in mind, I could have chosen any of these. I could have chosen that eigenvector to put there and there. I could have chosen anything as long as, for the eigenvector, as long as the second number is always 3 times the first. Oh, there's that drilling. Okay, let's finish this off. Lastly, I have a bit more of it. Well, this is all pretty abstract, but even a bit more abstract. Find the values for A in this matrix if one of the eigenvalues is 12. All right, so if one of the eigenvalues of 12 is 12, keep in mind there's usually 2. If one of the eigenvalues is 12, then I know the determinant of A minus the eigenvalue, which is 12, times I must equal 0. And so what does this mean again? It's this minus 12 times the identity matrix. So it looks like this. It's 8a plus 4, a plus 1, 5. It's this minus 12 times the identity matrix is 12, 12, 0, 0. And so this is just subtraction. So it's 8 minus 12, so negative 4, a plus 1, a plus 4 down here, and negative 7. So this here is this here. And I know that the determinant of that must equal 0. That's the definition of what an eigenvalue is. So let's look at the determinant of this. The determinant of this is negative 4 times negative 7, so 28, minus a plus 1 times a plus 4. That's the determinant. And again, if it's an eigenvalue, that must come to 0. And so cleaning this up, I get 28 minus a squared minus 5a minus 4 equals 0. Rearranging things so I get my a squared's positive, I get 0 equals a squared plus 5a minus 24. I want to solve for a. Let's hope it factors. It does. How convenient. I get factors of a plus 8 and a minus 3, which means the solutions for a are positive 3 and negative 8. Those are my 2 solutions. And so for those 2 values, my eigenvalues are indeed 12. All right, before I end this, thankfully, of all the lessons we've had a lot of abstract lessons, and we're only halfway through this lesson on eigenvalues and eigenvectors. It is quite abstract. The words are a bit of a mouthful. Just keep in mind the 2 key parts right here is the definition of an eigenvalue, which is generally we figure out first. It's where this equals 0. And once we know that, we can then solve this equation, which is matrix algebra, to find those eigenvectors. And keep in mind, in general, if we're looking at 2 by 2 matrix, there are 2 different eigenvalues, but for each of those, there really are an infinite number of eigenvectors. Let's stop it here.